he's behind the curtain. Yeah. It's too bright for you. You just look at the screen, maybe.
Or maybe you can just leave this space.
Do you have a solution to that, or no? I mean, they're the curtain. I think they're complaining about the light is too bright. Okay, sorry about that. So, why this one? Okay, proceed. Okay, cool. Sorry for the technical delay. So, welcome to the first crypto session, pilot session, and without any further ado, we have. Sorry, this one is trying to catch up. That one's work. Have the first talk by Qipeng Liu on how now to build the quantum PKE Minicrypt.
Okay. Yeah, thanks for the introduction. I'm not. Okay, that's not working. How about the other one? Okay, so I'm sorry about that, but at least one is working. So you can look at the other one. Okay. So just to start with the talk is the motivation, the goal of the work is. We know that in classical cryptography, almost anything meaningful that requires some form of assumptions. For example, you at least requires NP is not equal to P to do some meaningful cryptography. And also we know that from a classical perspective, we know that different crypto applications, they seem to require different structures. And usually as a cryptographer, we want this structure to be as weak as possible. Okay, so the weaker, the better. So the goal of this talk is to understand the structures needed to obtain the most fundamental crypto primitives, which is called the public key encryption. Okay. So we'll start with the introduction of the two primitives that we're interested in this work. So and let's start with the picture, a landscape for the classical cryptography. So I've just listed 4 primitives. They are commitment, one-way function, public key encryption, and key agreement. Okay. So in a classical world, we know that commitment implies and is implied by one-way function. And this is usually what we call the Minicrypt, which are everything that can be constructed and can construct one-way function. So they somehow form so-called like a complete set. So we give it a name called Minicrypt. Okay. So this somehow captures the structure that requires to build certain types of crypto primitives. And on the other hand, we have other primitives like public key encryption and key agreement. They are very useful. They are the schemes that people use every day on the internet to doing communication, to doing encryption over insecure channels, like the public key encryption. So we wanted to understand their structure. What is the primitives, or what is the structure that underlies these assumptions for us to build public key encryption and to build key agreement. Okay? So the result by Impagliazzo and Rudish, they show that indeed public key encryption is a strictly stronger primitive than one-way function itself. So this is pointed out in the work by IR889. And they name it as so-called the cryptomania, which is like a world which you can do much more crypto than what you can do just in Minicrypt, which is like the green, everything inside the green area. All right. So let's just very briefly recap what are one-way functions and what are public key encryptions. So one-way functions are just basically a function which you can evaluate on any input efficiently. But when you are given an image, it is hard to invert. Okay, so from that picture, it's easy to go from the left-hand side to the right-hand side. But if you wanted to get backward, it's very difficult computationally. Okay. And what is public key encryption? So public encryptions has those 3 different primitives, procedures. The first one is you output a pair of keys. The public key for people to doing encryption, and the secret key for the server who wants to who can decrypt later. Okay. And the security says that any malicious party who gets the public key and gets a ciphertext from the people who encrypt cannot tell what is really inside, what is really under the ciphertext. Okay, so this is the security. And in adversary time-bounded, given PK, given CT, cannot recover what's inside the ciphertext. That's the definition for public key encryption. Okay, so as I mentioned before, the Impagliazzo-Rudish result says that public key encryption, this powerful primitive, cannot be constructed from one-way function in a black box manner. Okay, so in other words, this can be interpreted as public key encryption is not in Minicrypt, or Cryptomania is not in Minicrypt. Okay, and the idea about proving this is they basically show that relative to an oracle or a collection of oracle, which they use the random oracle, one-way function exists. So you can think about it as a random function. You can use a random function to be the one-way function. But with this random oracle, public key encryption does not exist. And what they do is they show there exists some eavesdropper or adversary who can break the security of the public key encryption. Okay, so we all know that quantum information can reshape the landscape of crypto and can reshape the landscape of computation. Okay, so this was first observed by everybody knows the quantum key distribution, but more recently it was shown by Krasmer that commitment and one-way functions are not equivalent. So Krasmer showed that commitment is actually has a very strong evidence that it is a strictly smaller set than one-way function. Okay. So in this work, we care about whether the similar thing happens to one-way function and public key encryption. Okay. So for example, does there still exist such a barrier which separates one-way function and public key encryption, just as what they are in the classical setting, or if they are simply equivalent to each other and kind of like makes things even better for us because we want less structure, all right? And this is the question we're going to ask in the work. And we answer this question from different perspectives. Okay, does quantum PKE exist in Minicrypt? All right, so the first question is, what is quantum PKE, right? Because now you introduce quantum powers to your protocols, then the power can be from the computation side or can be from quantum information, okay? So again, let's record the definition of public key encryption. Still 3 procedures: output, PK, SK, CT, and message, okay? So first of all the procedure, the algorithm, the generation, the encryption, the decryption, they can be quantum algorithm, meaning even if they are generating classical keys, classical ciphertext, they can still be a quantum powered algorithm, can run like arbitrary quantum circuit. But on the other hand, there's something even more interesting is you can make those keys being quantum, or even the ciphertext being quantum, even if the message itself is classical. And this may enables quantum public key encryption from one-way function, make it possible. Okay, so that's kind of like some caveat about like defining, or some variance about how to define quantum public key encryption. Okay, so and indeed we do see a lot of different works try to define quantum public key encryption with quantum public key. So this was first started by some conceptual ideas by Molimai and Yamakawa, and then there are a bunch of works really constructing quantum public key encryption schemes with either quantum public key, and either quantum ciphertext or classical ciphertext. They have different forms of security. Okay, so this really can be demonstrated. Okay, and there's some caveat with those constructions, but for this talk, I'm going to skip those caveats and just go straight to the separation or the result. Okay, so let's start with our first result. So our first result says the following. So if we only consider quantum public key encryption with a key being classical, okay, so there are public keys, secret keys are both being classical. They are classical strings. And even if the ciphertext can be quantum, so it can be quantum ciphertext or classical ciphertext, then perfect complete quantum public key encryption, meaning you can always perfectly decrypt a ciphertext as long as the ciphertext is generated honestly. So this kind of quantum public key encryption does not exist in the quantum random oracle model. And there's a caveat for the theorem, is if the generation only makes classical queries. Or in other words, if the generation algorithm is only a classical algorithm. So you have algorithm generating the keys, the algorithm's generation can only be a classical algorithm, but both the encryption, the decryption can be a quantum algorithm. And this kind of schemes cannot be built from solely based on one-way functions. Okay? This is the first result. And the second result, we improve, still result 1, it's called result 1.1, is a result that's improved the previous one, which we relax this requirement. So let's get back to the slide. which requires the generation algorithms only being a classical algorithm. But now we can replace that with a specific conjecture on Boolean functions. And as long as you assume that conjecture is true, then you can rule out any quantum public key encryptions with classical keys in the random oracle model. Okay? Unfortunately, this conjecture is a bit long, even if it's simple to describe, but you have to define all the related notions for Boolean functions. So I didn't put it here. And another reason is because the next slide. Okay? So the next slide is the ongoing result. Like when we submit the manuscript, we don't have this particular slide. But now we can fully show that the theorem 1, which is perfect complete quantum public key encryption with classical keys, does not exist in the quantum random oracle model without any caveat. Okay? So in other words, if you only want keys to be classical, then, I mean, this is like the most convenient way to build public key encryption, then you cannot build that from only one-way functions. So you still need some structures in the primitive, in the assumptions. Okay? And how we do it? We basically prove the conjecture mentioned in the previous slides, and the paper will appear soon. So this is basically a quantum version of the Impagliazzo-Rudish paper. You can interpret it as quantum minicrypt is not in quantum cryptomania. All right? So that's for the first part, quantum public key encryption with only classical keys. Okay? And so I mean, you can look at this picture, and now the picture becomes more complete. So not only there's a barrier between the green and the blue area, there's also a barrier from the green and the yellow area. So you cannot build public key encryption from one-way function if you restrict the key to be classical. Okay? And now let's move to the second part, which is the quantum public key encryption with an arbitrary quantum keys. Okay? So first of all, we have to define the security because now the public key is being quantum, but there's some caveat. For example, getting a quantum key, you use a quantum key to do encryption, and the keys might just disappear. So you have to have access to multiple keys to make the scheme meaningful. But that also means the adversary should have the power to get access to multiple copies of the keys. So in this case, because this public key has to be a quantum state, the security has to be defined in this way. Well, not only the adversary only gets one copy of the public key and the ciphertext, but now it gets multiple copies of the public key. And this T here can be like any polynomial, which can depend on the running time of the adversary. And the goal is the same, try to reveal what's really underlies the within the ciphertext, covered by the ciphertext. Okay, this is the definition. Okay, so and this is our second result by formally define what is a quantum public key encryption. We say that, so our theorem says that perfect complete quantum public key encryption with quantum public key does not exist in the quantum random oracle model if the generation algorithm only makes classical queries. So it's the same as the first result, result 1, but here we still have this restriction of the generation algorithm makes only classical queries. So if you wanted to overcome it, you have to make sure your generation algorithm has the quantum power. Okay, so, and you may wonder, is that possible to get rid of this, this restriction? And the answer is no. So we show that actually our second result is tied to all existing quantum public key encryption schemes with perfect completeness. Okay? So first of all, we know that there are two different schemes. I mean, they are different in different papers, but they somehow have the same form. Well, this generation algorithms only make classical queries. They queries to the random oracle, and they try to get a random signatures for messages 0 and 1, and there are public keys of this particular form. Okay, this is like 1 over root 2, 0 sigma 0 plus 1 sigma 1. So it's a uniform superposition over message 0 appended with the signature for 0, message 1 appended with the signature for 1, and just like doing a superposition of that. And according to our second result, their public key or their scheme is not secure because you cannot get multiple copies of this. Sorry, if you look at this tensor T, you cannot get multiple copies because otherwise it is not secure. Okay, And our result is also tied to the other kind of quantum public key encryption with perfect completeness, which are the schemes in these other 3 papers. So in their construction, their public keys are quantum states. Okay, ignoring this pure state, just quantum states. And according to our result, I mean, they prove their security. So their generation algorithm must make quantum queries to the random oracle. So it inherently has the quantum power, which exactly get over the our impossibility result. Okay, so this is one example in the result in BGH plus, which, well, their quantum keys is a uniform superposition over input and the pseudorandom evaluation of pseudorandom function on that input. Okay, so all right, so I think I have 5 minutes. Okay, so let me just very quickly talk about the ideas behind that. So what we do here is to rule out this kind of quantum public key encryption. What we do is we reduce that to a key agreement protocol. Well, a key agreement protocol is like 2 parties querying to a random oracle. They can communicate messages to each other, and eventually they want to output a pair of keys which are identical. So, and the eavesdropper can look at this transcript and can also query the random oracle. And eventually, the eavesdropper's goal is to output a key, okay, and the key. And he wants to match this key with whatever established between Alice and Bob. Okay? And we can see that a public key encryption scheme really implies a key agreement with 2 rounds. And what is that? Because you can run Alice to generate the public key, sending public key to Bob. Bob just pick a random key, KB, and encrypt that and sending that to Alice. Okay? And finally, both can get this KA-KB, and as long as the scheme is perfect complete, you have KA equals to KB because the security, because the correctness of the public key encryption. So you can reduce that to a 2-round protocol, and furthermore, we can, for the purpose of the talk, we only look at this kind of special schemes. Well, it's 2 rounds, but it's literally just 1 simultaneous round, just to make our analysis simpler. Okay. And all right. So, and what is the idea to rule out this particular scheme? So the idea, we kind of like look back to the idea that's in the work by Impagliato and Rudish. So what they show is, both parties query to the random oracle, and they may have some overlaps if you look at the random oracle. So on the picture, those black nodes are the overlapped queries by Alice and Bob. So their idea is, as long as this eavesdropper can completely query those overlaps, then you can break this protocol. And the idea is basically, these overlaps are the resources that build correlation between Alice and Bob. So as long as you can break the correlation, you can perfectly sample the Alice's view. In other words, you can sample the key from the Alice. So the key must be equal to whatever on Bob's hand. So it's really important to find a way you can sample Alice so that it matches with whatever has in the Alice, the real Alice's hands. Okay, so this is kind of like our idea. So it's 2 minutes. So let me kind of like looking at the proof in the Impagliato and Rudish paper. So what they do is they find a strategy which they can query Alice and Bob's to make the query so that the query, the intersection query of Alice and Bob are covered by the eavesdropper. And then having that, they can sample the view of the Alice. So basically, they can say that this is by condition on whatever eavesdropper already did, the distribution, the view of Alice and Bob, they become independent to each other. So I can sample Alice's view. So what we do here is we translate that using the language of mutual conditional entropy, conditional mutual entropy, and we can perfectly do everything in the quantum setting. So what we do here is we can find a strategy which by querying, by querying the random oracle, the conditional mutual information between Alice and Bob, condition on whatever eavesdropper has, is very small. It's like as small as epsilon. And then eavesdropper can sample whatever Alice has using the information it has, which relies on the result by the approximate quantum Markov chain by Fawzi and Renner. Okay? And eventually, whenever we can sample the view from the real Alice, we can establish the key, because now the fake Alice and the real Alice, if you look at this picture, they have exactly the same distribution. So you have the KA prime, which is the sample from the fake Alice, equals to the key owned by the real Bob, which equals the key which is owned by the real Alice. So after doing all these three steps, we can establish the adversary, which can successfully recover the key by making all these quantum queries. Okay, so so there's a couple of open questions. So the first one is we didn't mention the caveat in the theorem statement is we have to make sure these encryption schemes are perfectly complete, which we didn't mention in the talk. So there's a technical caveat that's hidden inside the theorem statement. And also, we didn't talk about what is the caveat inside the quantum public key encryption, right? So when the key becomes quantum, you have to make this key somewhat reusable to make it a meaningful scheme, okay? And is that possible? We can rule out all quantum public key encryption with the key being quantum, but has certain form of public reusability. And we didn't do that. I think this is a very interesting question. Even to define what is public reusability is a very interesting question, not to mention like to rule out such possibility or give a construction which enables public reusability. Okay, so I think that's it.
What's the difference between the idea of reusability and the clonable?
So that's a very good question. So clonable means you can get like multiple copies of the same key, but reusability means maybe it's no longer the same copy, but you can still use that. You know, like you get a PK, you encrypt the message, you get a PK prime, but the PK prime can still be used to doing the regular encryption. So it's no longer the same quantum state, but you can keep using the other leftover quantum state to do the encryption. So we can somehow show, you cannot clone, but it doesn't imply reusability. So clone is like a weaker requirement. Yes.
I see. Thank you.
Thanks for the talk. So regarding the perfect completeness, is that the quantum-only feature, or was it also in the Impactliazzo-Rudich?
It's a good question. The question is like, we have this caveat about still having the perfect completeness. So basically, our proof, although it mimics the Rudich, like Impactliazzo-Rudich proof, but it's inherently different. And we don't even know if our proof method can be casted on a classical proof with imperfect completeness. So in other words, it's not just about the quantum, it's actually about the proof method itself. Yes. So even classical, we don't know.